Algebra 1, Investigation 2. In this investigation, we are looking at graphing, just in general, and especially being able to graph a relationship. We're going to be looking at both discrete and continuous functions based on different stories and situations. So let's just get right into it. A graph is a visual representation of how data change. Data is the plural here, and relate to each other. A graph can convey the numeric relationship between data, like time and distance. For example, Maria takes a beach trip. She stays at the beach all day before driving back home. As Maria drives to the beach, her distance from home increases. So we can see here in this graph, we have an increase in distance, okay? And then while she is at the beach, there's no change. She's still the same distance from home. And then once she starts coming back home, she gets closer and closer and closer until she's 0 distance away from home, which means she arrived at home. So here's another situation. We have the graph showing various speeds at which a horse travels. On the x-axis, we have time, since that is our independent variable. And then speed depends on the time for this horse. So it is our y, so it is our dependent variable. It says, use the graph to complete the table. Describe the horse's speed in each of the time intervals as increasing, no change, or decreasing. So let's look at this. From 0 to 10 minutes. What it's asking for is from 0 minutes to 10 minutes, what is happening with the speed of the horse. And in this case, we see a flat line. What we can say with this one is that there is no change. Then it asks for 10 to 18, which means from this point to this point. Well, we have a line that's going up, and since we read it from left to right on a graph, we would say this is increasing. From 18 to 38, we have this top part, which has no change since we see a horizontal line. Then from our 38 minutes to 40, we have a very rapidly decreasing line going down, negative slope. And then from 40 to 50, there is no change. What this is basically saying is that from 0 to 10 minutes, the horse stayed at a constant speed, and then it sped up from 10 to 20. Then it stayed at that higher speed for a while. Then it really slowed down to that kind of walking speed again, where it stayed for the rest of the time. So we can show, using a graph to show that data change. When drawing a graph to represent a real-world situation, these are the things that we should follow. Appropriate intervals for the units on the axes is really necessary. Be sure to space the intervals equally. This graph up here with the horse's practice run would look very different if I had from 0 to 10 and then 10, and then the next one would be, let's say, 18, and then we jump all the way to 40 and then 50. This would be very different. We have to have consistent intervals to make sure that we are representing the graph correctly. And then only use values that make sense, such as positive numbers of books or whole numbers of people. So let's try this one out. Customers at a local grocery store pay $3 per pound for pecans. They can purchase the pecans in fractions of a pound, meaning I can buy 1.5 pounds, I can buy 2 3/4 pounds. I can really buy any amount that I want. So number 2, should the graph representing the situation display negative values for pounds of pecans? Well, can I buy a negative 1 pound of pecans? And we would say that makes no sense at all. And so no, of course not. We cannot represent negative values for the pounds of pecans, because that would mean like we owe somebody pecans or something. That would be a very odd situation. Number 3, what is a reasonable maximum for the number of pounds to graph? Well, this kind of depends on what you're thinking about. If you are just an individual person buying pounds of pecans, maybe you would only go up to, 5 pounds or 10 pounds. But if a restaurant that specializes in pecan pies buys these pounds of pecans, maybe you would go up to 100 pounds, who knows? So it depends on the situation, but let's say we're talking about an an individual. And let's say we go up to 10 or 15 pounds, something like that. So what is the cost of purchasing 1 pound of pecans? Well, it says that in the example up here, 1 pound is $3. So how much is 4.5? Well, if each of those pounds is $3, we would do 4.5 of them. So 4.5 times 3. And you should, of course, work that out for yourself, but you should get something like $13.50. Let's draw a graph to represent all of this information. And what we have to really check on right here is what goes on each axis. And I'm only graphing the positive money and positive pounds of pecans here because negative money, negative pounds doesn't make a lot of sense. But let's make sure that we know which is which. On our x-axis, we want the independent one. So let's figure out what depends on that. Does the dollar amount depend on my pounds, or does my pounds depend on my dollar amount? And the more logical one of the two is to say my dollar amount depends on the pounds. So if my dollar amount depends on it, then it goes on the y-axis, my dependent variable, and the amount of pounds is independent because I get to choose how many pounds of pecans I want. I don't really get to choose how much money it is. You can make an argument for the other, but overall, most logical is in this setting. Pounds on the x-axis, dollars on the y. And then we can start labeling. We can think about how many pounds to put on here, depending on what you want to do. I'm just going to go by ones here so that I have enough room for, let's say, 8 pounds. That should be plenty for an individual person. Maybe they're doing some trial runs of pecan pies. And then for dollar amount, if 8 is my highest amount, that would cost $24. So I should go up to at least $24 on my y-axis. Let's say I go by 4s. Something like that. So 4, 8, 12, 16, and 20. Okay? Now you could easily go by 3s here, and that would absolutely make sense as well. Probably even more sense than 4s. But let's just graph some of this information. And you know what? I'm changing my mind. I am going to go by 3s here. It'll help me graph, especially when I don't have graph paper here. So, oops. Here we go. 3, 6, 9, 12, 15, 18, and 21. There we go. So that I can graph 1 pound is $3, 2 pound is 6, and all the way up. And you will see as you continue graphing that you will have a line that looks like this. I shouldn't go any further past my 0, 0 point, but I can go further into the future, so I would put an arrow on that right side of the graph. This is how I'd represent this situation with pecans. All right, going on, let's look at some more information and then a new situation. So the cost per pound data model in the graph, that's a continuous model. So continuous data are data where numbers between any two data values have meaning. What that means is that with this solid line that I have, any point that I have on the line, let's say it's right in between right there, means that I could have 3.5 pounds of these pecans and a certain dollar value for that, which I can find by going that way. Every single point that I have on this line, wherever I want it to be, there should be an actual value to it. So we show that with a solid line. That's called continuous data or a continuous graph. It's a graph that has no gaps, jumps, or asymptotes. So asymptote is a line that you can't cross and doesn't have any values there, just so you know. Data that involves a count of items such as number of people, something that has to be whole numbers like people or books or things like that, we call discrete data. Discrete graph is made up of separate, disconnected points determined by discrete data. So for example, a sheet of photos at an automatic photo booth cost $5. Patrons can only purchase full sheets of photos. The photo booth can print up to 10 sheets per patron. What will the graph look like? Well, do we have continuous data or do we have discrete data? In this situation, if I had continuous data, then I would be able to say I can buy 3.5 sheets of photos. In this case, that's not true. We can only purchase full sheets of photos. So this is discrete with dots on our graph, just dots. We don't have a line that connects them because that line would mean that we have fractions of our sheets of photos. So number 7, continuing on, what is the least number of photo sheets for purchase? Well, I don't have to buy photos, so I would say 0 is the smallest amount. I wouldn't go into negatives here because that doesn't make any logical sense. But what's the greatest number of sheets? Well, it tells us in the information that I can buy up to 10 sheets per patron. So let's draw a graph to represent this. And we have 2 different variables here. We have money and we have number of photo sheets. And I would say that the money depends on how many photo sheets that I buy. So money goes on the Y and number of sheets goes on the x-axis for our independent variable. And I can have up to 10 sheets. So I'm going to put 10 different spaces here. All right. And I'm just going by ones just to make it easy to see. I would encourage you to, of course, be following along with me, but on a piece of graph paper is even better. So on my money, each one of these costs $5. So I'm going to go by 5s and make sure that I have room for $50 here. All right. So now we can graph. This one is starting to look like what we had earlier for the pecans, but in this case, we don't have that connecting line. All we have are these dots that represent the number of photo sheets that I can have. So 3 goes to 15, 4 goes to 20, 5 to 25, and so on and so forth. But these dots are all that I'm going to have here, okay? All the way up to 10 for $50, but I'm not going to connect them. I can have 0, 0. I can have 10 sheets for $50, but I can't have 4.5 sheets for 45, or 4.5 sheets, or 6.5 sheets. I can't do that, so I only have the dots, so I'm not going to connect them, and that's what we would do to represent the situation. All right, just a couple more situations here. We're going to describe some graphs. So number 9, use the graph to describe Maura's hike on Windy Hill. In the description, use phrases like increasing, no change, and decreasing. And we see that we are relating time and elevation. I'm just going to verbally explain this one rather than trying to write it out here. So how I would describe this is that when she begins her hike, the elevation stays the same. And then after a small period of time, the elevation starts increasing, so she's going up a hill. Then it looks like she gets to the top of the hill and maybe she sits for lunch and stays there for a while, or just walks around the top of the hill. After a while, she decides to go back home, and so she starts going down the hill again. So something like that would be able to represent what I see here. What I see is no change, so no elevation gain. Then she's going up the hill, she stays on the hill, and then she goes down the hill. So a graph represents the relationship between the two quantities, time and elevation. Well, number 10 says describe another set of data that could relate to the hiker's time. So instead of elevation here, what else could we use? Well, you probably have a few different ideas of what it could be. Let's say my example for this is something like maybe her heart rate, how much her heart is beating per minute. And maybe she's not exerting herself, so it stays the same for a little while. And then she starts walking quickly, and so her heart rate goes up, and she stays at that heart rate for a while, and then slowly her heart rate goes back down, maybe as she's sitting down. So her heart rate returns to a resting heart rate. There's a lot of different things that you could do here. Think about some of the different options other than heart rate that you could relate to time. All right, and then the last situation here for this investigation. Many quantities can be measured and compared, such as a plane's traveling speed and its altitude. Commercial airplane travels at 600 miles per hour, typically flies at a height of about 6 miles. The graph shows the flight time and the altitude of the airplane. So number 11, what is the plane's altitude at the beginning and end of its 6-hour trip? Well, if we look at this graph at the beginning and at the end, we would say that its altitude is 0 miles because it begins, of course, on the ground, at the airport. Number 12, describe the plane's flight in the first and last hour of the trip. So from 0 to 1 hour, and from that, there we go, there's my 1 hour, and then from that 5 hours to the end. So those first and last hours. In the first hour, it looks like it's increasing in altitude pretty rapidly. And similarly, in the last hour, it's decreasing rapidly. I would imagine this is when it's trying to get up to the correct height and when it's going back down to the tarmac. And lastly, number 13, explain why the graph of the plane's flight is relatively flat between the hours of 2 and 4. Well, typically when you're on a flight, you stay in the air for some amount of time at that altitude. So between 2 hours and 4 hours here, I would say that it stayed at a same altitude as you're flying from that place to place. No need to go up or down in altitude unless there's weather to avoid. In this case, no weather to avoid, so they're staying at the same height, at that same altitude. All right, well, I hope this investigation has you thinking more about how to represent situations in a graph form, and I hope this video helps with your homework and for studying.